Hello class, I'm here to talk about, this is Dr. Viv and I'm here to talk about moments of inertia today. And particularly I would like to discuss how moments of inertia may be found through the techniques of integration. So we start as before in my earlier video on the center of mass of objects. I had a straight rod. We'll take that same example. So you put the rod along the x-axis and it's placed so that the left end is at the origin and the right end is at x equals L, and we wish to find the rotational inertia of this rod about the y-axis. In other words, you keep the y-axis as your axis of rotation. So I'll keep this pen to demonstrate that it's an axis of rotation, and then this rod rotates about that axis like this. Okay, so what we're trying to find is the degree of difficulty of rotating this rod in that manner. So the procedure for finding the moment of inertia is very similar to that for finding the center of mass, so it may be a good idea for you to review that first video. Let's call this mass element dx, and it's placed some distance x from the left end. The normal definition of moment of inertia, which I'll call I about the y-axis, would be the sum over all the mass points mi at some distance xi squared. Now it's x because of the variable. It could be any other variable. For example, it could be some distance r if you're talking about a random distance, but in this case that distance is x. Now the usual procedure for going from a discrete mass sum to a continuous mass sum remains the same. You integrate like that, where dm is the mass element. Now this mass element, which I introduced for the center of mass video, is the same mass element which is got by using what's called a linear mass density. So I'll write that here. Lambda, whose definition is the following: it's the rate of change of mass with respect to distance. So as you saw in the earlier video, this has units of kg per meter because mass is measured in kg and length in meters in the SI system. So in this particular example, the variable of integration is x. So we have to find some way of converting dm to dx, and that's what makes that possible, this linear mass density. Now lambda in general could be a function of x, so we'll just call it lambda for now. Solving this for dm, I'm going to get dm equals lambda dx. And now I can find the moment of inertia by substituting lambda dx for dm in that formula. So let me try that. Moment of inertia about the y-axis is equal to the integral from x equals 0 to x equals L of x squared lambda dx. We can try this out for a couple of examples. So here's example 1. Let's try the case where lambda equals lambda naught, which means it's a uniform rod, nothing changing. For example, the aluminum rod that you had in your lab is a good example. It was a uniform cross-section throughout and nothing changed. So let's try that. if you do this, then the moment of inertia about the y-axis is going to be integral 0 to L x squared lambda naught dx, and you'll take the lambda naught outside since it's a constant. Integrate and the result is lambda naught L cubed over 3. Now it's usually a good idea to compare this or write it in terms of the total mass. So let's also try to find the total mass of the rod. That's going to be the integral from x equals 0 to x equals L of simply dm. So that's going to be integral 0 to L lambda naught dx. Take the lambda naught outside. The integral of dx is just x. So that's just lambda naught times L. And now you can express this moment of inertia in terms of this mass. So that's the next thing I'll do. The moment of inertia, Iy, is equal to, what I'm going to do is I'm going to write this 1/3 lambda naught L cubed in a special way. I'll write it as lambda naught L times L squared. Now you can see that lambda naught L is just the mass, so I'll write it as 1/3 ml squared. And that is the standard result. If you go to your formula sheet, you should be able to find it. It's a formula sheet, moment of inertia of a thin rod about one end. Let's try another example, and this would be one where the moment of inertia actually is different because lambda depends on x. So let's try that.